Okay. First of all, this is like a skeleton model. An original sine wave, let's say g at x, is just equal to sine at x. Okay? So in other words, your a is still technically there. It's 1. Your d is 0, k is 1, c is 0, but we'll get all into that. What's important is you have to know how to graph a sine wave to start. So usually we use degrees. Okay? We'll say 90, 180, 270, 360, and it also goes the other way. Technically, this is 450. That's what draw it. This is 450. And an original sine wave, let's say it goes to 1, it goes down 1. So a sine wave, this is our sine, I'll draw it in black, starts at the origin. These are key points in it, okay? Has a point at 1 and 90, 0, 180, negative 1, or 270 and negative 1, 360 and 0, and then it continues the same pattern. So essentially the wave goes like this, and continues, okay? Same idea as if you were to go backwards, you just kind of continue that pattern. It's just a little reverse on positive 90s at positive 1, negative 90s at negative 1, and so on. Not the best draw, but there you go. And the idea behind this is, think of it as if you're drawing a circle, okay? And let's say we have flat line, flat line. I know it's not perfect, but let's just say we're starting here, okay, on a circle.
Yep.
But the radius of this circle we're going to say is 1, okay? So this radius is 1. So from here to here is 1. When you move in a circle, if we start here, this is a 90-degree shift. So we go all the way up. From our line here, we're now 1 away, which is the same idea here. After a 90-degree shift on the circle, we're at 1 and 90. So we're at the top of the circle. If we continue down, we get to 180. 180 again is on par with where we started, so our y is 0 again, but our distance is 180 away. Now, instead of coming back like a circle does, where we're coming back towards where we started, this one just continues, so you can see it like almost like a heartbeat. You can see exactly where you are.
Okay.
So at this point, because the radius is 1, you're at negative 1. So once you're 270 away, it's the same idea. We go up, down. Once we're 270 away from the origin, we started here and came all the way around, we're at negative 1 on the y-axis. And finally, on a normal circle, when you get to 360, you're usually back where you started, and you're back at 0. Now that would be considered the period of the function.
Okay.
Have you heard of that before? So the period of the function is how long it takes it to do a full rotation. So let's just say we didn't have the left side of the y-axis. Let's just say we start at the origin. Okay, we go up, down. Now technically we're back at 0 again, but if you look at the left side just a little, we were coming up when we got there. This time we're going down, so we haven't completed a period. So we go up, down, down. Once we're coming back up again like we were there, and we're back at 0, that is an entire period.
Oh, okay. Yeah.
And in other words, it just completes an entire rotation of the circle. This thing's going really slow. But it completes an entire rotation of the circle.
Okay.
So that's what one period of the function is.
So the period would be 360?
The period's 360,
Okay.
yeah. Of a sine wave and of a cos wave, it's 360, the period, okay? This is specifically a sine wave. That's the period of an amplitude of the function is how far from the equation of the axis. And the equation of the axis will be, I wish I had colored lines. This way. Equation of the axis is the middle of the wave. Okay. Now it's pretty easy to tell the middle of the wave here is obviously going to be 0, and from this one here it's obviously going to be 0 again, right? There's the equation of the axis. Excuse me. Your amplitude. The amplitude of the function is how far from the equation of the axis the peak and the trough are. A peak is the highest point, which is here, and a trough is the lowest point. Now for this to be a function, the peaks and the trough repeat. So you're going to have many peaks. So if you notice we have 1, 2, 3 different peaks, and in this one we have 1, 2, 3 different troughs. Now these technically go on forever. This wave just keeps going and going and going. Okay? So once again, the amplitude is the distance from the equation of the axis to the peak, and it'll also be the exact same distance to the trough. So pretty much it's from the middle to the top and the bottom. Now, because we're using 1, this is our original one, the amplitude of this is 1. So we'll say amplitude is 1. And that's the same idea with the circle I showed you. If the radius is 1, well, obviously the amplitude is going to be 1. Okay? The amplitude can change, and so can the period. But our original one, our amplitude is 1, our period is 360. Let's get that down too. Period for our original one is 360. 60 degrees. Okay. Does that make sense so far?
Yeah.
Okay. What we're going to do first is I'm going to deal with C and D. Okay? That'll be easiest, I think. So, G at X equals, I'm going to leave A and K out for now, just because they're a little harder. We'll get to it. So I'm only going to do 2 for now, minus D plus C. Now these have the same idea as, I'm going to change the colors. When we were doing, if you remember, we were doing transformations of parabolas. C deals with shifts vertically on the y-axis. So C, pretty much, if C is greater than 1, that is not a 1. There you go. If C is greater than 1, or in other words, it's positive, you shift upwards.
Yeah.
So shift up. Okay. C is less than 1 or negative, shift down. Okay. D, if you remember, like in the transformations, it's the opposite idea. Right? It deals with left and right, so shifts on the x and y axis. The only difference is if you have this whole part here, including this negative, it says positive 5.
Then it's negative.
You go in the negative direction, and if it says negative 5, you go in the positive direction. Okay. Yeah. Now, did I show you technically that's because there's a negative in front of this? Yeah. So you understand that idea? That. Okay. Good. So let's just keep it as our. Let's just keep our rules here. So in other words, if D is greater than 1, so if it's positive, you shift left. Yeah. So I'm going to say if it's positive, you shift left. And if D is less than 1 or negative, you shift to the right. Okay. So C and D are very similar to each other. C's y-axis and D's x-axis. So I'm going to put x-axis here. So you know that. And y-axis. Okay. So we should probably do an example of that. We'll try to do 2 in 1. I think you're smart enough to do 2 in 1 instead of 1 at a time. So let's say G at X is equal to sine X, and I'm going to say. Now, the other thing is, if you notice, I used the numbers like 5 there. Because you're working in degrees, they're probably going to go by increments of either 30, 45, 60, 90. It's just so it's easier to work. It can technically go by 1, but then my scale is way too large. So I've gone two units, and it took 90 degrees, I said. If it told me to move like -1, I'd need to like make this graph so much more delicate, so much more intricate, okay? So let's say minus 90. But on our x and y, it's a little easier. We can use relatively common numbers. We're going to play +3, okay? So when we take a look at that, negative 90 means we're moving which way?
Right 90.
Right 90 degrees, and positive 3 means we're moving
upward.
Okay, so we'll do the blue shift first, okay, and then we'll do the red shift, and that'll be our final answer. So because it says negative 90, like you said, we're shifting 90. It's always good to draw the original model. So try to get this memorized, okay? Once you draw the original model, it's pretty easy. You just take this point, and because we're going 90 degrees to the right, on the same y, I just move to the right 90 degrees. So this point here, I shift it over 90 degrees. This point here, 90 degrees. This point here, 90 degrees. And I can do that with every point. Our origin comes over. This becomes the new y-axis. This goes there. Do you understand what I'm doing? Yeah. And then, technically, there's nothing to the left here, so we'd have to complete the pattern. So our first shift ends up having a graph like this. I'm going to add some extra dots. That's the idea. The entire graph, if you notice, has shifted 90 degrees to the right. Okay?
Yeah.
So we've shifted the whole wave 90 degrees to the right. So that's our first one. Check, we got that. Second shift, +3. I take the entire graph and I just move every point up 3.
From the original or from?
From our new spot.
Okay.
So our blue one. So my blue one. Here we go. This is at 0. I go up 1, 2, 3. There we go. This was at -1. I go up 3. 1, 2, 3. Oh, sorry. It goes by 2s. 1, 2. Sorry, I drew the first point wrong because I didn't realize I made the scale by 2. So if this is 0, this is 1, 2, 3. Okay? Now I'm at 3. -1, this is 1, 2, 3. And I should write the other numbers in there so it makes sense to you. So this is our negative, not -2. 3.
How come you do it by the new one and not by the original?
I could have done the first shift by the original, but think of it now that we're moving in steps. So think of the blues as this is one wave, and they've told me to make 2 transformations.
Okay.
So I still only have one wave. It's just moved differently on the graph.
Okay.
So think of it like when we were doing our parabolas. Remember how there was 3 different shifts, but it's still only one parabola. I've just moved it somewhere differently in the graph. So I could have done one at a time. You're right, I could have just done the blue one, but I decided to do 2 shifts at the same time. So we had to go left and right, and we had to go up and down. So all it is we took the original graph and we've moved it right and left and up and down. So it's now somewhere else.
Okay.
Does that make
I think so.
kind of? Okay. So we have our numbers there. Again, all of our points. This one's at 0, so we go up 1, 2, 3. This one's at 1. So when I go up 3, I'm going to be at 4. You can almost use math just to solve it. 0 plus 3, -1 plus 3 is going to be 2. 0, 3, 1 plus 3 is 4. And if you notice, we're pretty much just going to, I can almost just walk through this completing the pattern myself. So this is actually our new graph from our original. So our graph's at this point. So this equation here, this is what represents it right there. The blue was just the first shift, and the red was the second shift. I went up +3. Okay? That's because that's what our C was. Our C was +3. So the period and the amplitude are the exact same. Period's still 360. Amplitude is still 1. All I've done is I've moved from the black one to the red one now.
Mm-hmm.
I just did it in 2 steps because there's 2 shifts. Does that kind of make sense?
Yeah.
Okay, those are the easier 2. Let's try.
Could you have done it in like 1 and gone over 90 and then up 3?
Yeah, I could have done that.
Okay.
I just drew this so. Yeah, I just drew this so I had a reference point.
Okay.
If you can do it all in one shift, go for it. You don't need to draw the other one. You might have a teacher say, like she'll give you, your other 2 variables too, and technically that's 4 movements. She might say draw each step one at a time because she wants all the marks. But you can do it in one. It's really not an issue. Okay, let's go to the next page. Okay. Put up another graph. Okay, so again we have our formula. G at x equals, what's the letters used? A sine k x minus d bracket plus c, right? So we've dealt with our c and d. We're going to focus on our a right now, okay? So I'm not going to add a c and d to it. I'm just going to focus on a, and then we'll try to put it all together at the end. So again, we have our normal one, which is, and we'll draw it out, 90, 180, 270. These are all degrees, right? 360, 450, and it goes in the negative direction. I always find it personally easier if I have almost like my base model to work off. And we go up 1. And this one, I'll put it here. We'll go by 2s. Okay. -1. So again, origin 90, 180, just like drawing a circle, right? And then we just continue the pattern. You'll get good at drawing the original one after a while. So a wave. And remember, it's a wave. You'll plot these points. Obviously, you could connect them all with straight lines.
Yeah.
But don't quite do that. Your teacher is not drawn properly. Okay, so this is our g at x equals sine x. That's what that is. That's our original. Now we're dealing with just a, so we'll put a in. We'll do it in red. Green. Now let's do a sine x. What that does is an amplitude shift. So remember our amplitude was 1. Whatever the number becomes, so let's say it's 4. Okay, so our new equation becomes g at x equals 4 sine x. All that happens is our amplitude has changed to 3, 4, 5. -2, -3, -4, -5. So now this one's a little harder to grasp, but our zeros are going to be the exact same. There's going to be no change, okay? So my zeros are still going to be here, 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 and here. And the reason being is because when you multiply 4 times 0, it's still what?
0.
0, okay? Now, instead of our 1, I'm going to multiply that 1 by our new number 4. So that's going to be my new y-axis at that point. So what is 4 times 1? 4. So my new point is at 4. And then I come back down because 0 times 4 is 0. What's negative 1 times 4?
Negative 4.
Negative 4. So here's our new y-axis.
Oh God, it's huge.
Okay, yeah, it's extremely stretched. Okay, same idea. Negative 1 and 4, 0, 4, and negative 1 and 4. So this one's a lot harder to draw for me. By freehand, it'll be way easier for you with a pencil. Or not as good on the computer, but the amplitude. The amplitude of this. Okay. You notice the amplitude of this has changed. It's gone from being 1 to having a new amplitude of 4. So it's really easy actually to find the amplitude. Whatever a is equal to is the amplitude of your wave. Okay. So in our original one, technically there's a 1 there, and that's why our amplitude is 1. Okay. Does that make sense?
Yeah.
So this is stretched. The same can be done. And I'll quickly do one in. I'll do it in blue for you. Let's say we had g at x equals a half, just because I can draw a half easy. Sine x. Same idea. A half times 0 is still going to be 0. So those points are still all going to be the same. Okay. The difference here is going to be our half. So 1 times a half is half. So this one has been compressed by a factor of a half. So if you notice this one, it's a lot smaller than what we'd drawn before. Does that make sense?
Mm-hmm.
The amplitude is changed. The amplitude is changed to a half instead of being 1.
Okay.
So that's what your A transformations are. Okay.
Yeah. It's not too bad.
Not too bad. Let's go to K. Okay. So shifting K. Again, I'm not going to do the other ones all together. I'm just going to do these individually. So in other words, this will look like sine of, and let's do it in green. Let's K. And it'll be K times X, because we're not going to have any D. Okay, so that's what our D is. It's just a K shift. So, just so we're used to it. Actually, what I'm going to do now, I'm going to change the scale a little because we're dealing with the period. So our X and Y is going to change a little. I'm going to stretching, technically compress it. So instead of going up by 90, I'm going to go up by 180 here. Okay, which means our original one's going to look just a little different from before, but it's still technically on the same numbers. What's 360? What 4?
2.
Is it 450? No, that's the next one. I gotta go up by 8.
Oh.
5.
40.
Yeah, that's it. 540, 720. Those are all the snowboardings, and then 180 or 1080. That's it. 1080 snowboarding. I remember that game. 40, 720. Right. I'm going to stretch this a little, like the height of it at least. I'm going to put 1 to go by 4. And really, you can draw it any way you want, right? And it's going to make it look different, but technically you're all on the same points. Okay? So, my origin's still 0, 0. But normally at 90, I'm at 1. This is where 90 is. Here's my 180. Here's my 270, 360. So there's a period already. If you notice, this looks a lot more stretched and compressed. But it's actually the exact same wave. It's just because I've made my scales different that it looks different, okay? So that would go back up here, here. So this is still a normal sine wave. This is still g at x equals sine x, okay? And let's do it the other way just so we have the entire pattern. And I think I'm a little better if I go left to right. Hey, all right. So there's our sine, okay? So we've drawn it, and like I said, it looks different, but it's actually the exact same way. What's happened now is we're having k shifts. So first thing we'll do is a k shift. Think of it like this. Because our normal period is 360 degrees, think of our new period is always going to be 360 divided by whatever k is. Okay? So that will be the new period. In this function here, k is 1. So 360 divided by 1 is 360. That's why our normal one is 360 degrees. And if you notice, that's one period there. Okay? Change it to 66. So this was the whole period. We went up, down, and we're back here, 360 degrees. Okay? Let's say we have a k that is less than 1. It's going to go differently. It's going to expand it if it's less than 1. And actually, sorry, let's do whole numbers. Might be a little easier to start with. So let's say we have g at x equals sine 3x. Okay? We don't need any brackets. Sine 3x. So what that means now is I take my 360 degrees and I divide it by 3. My new period is going to be 1, 2, 0. Is that right? Yeah, I should have used a nicer number. New period is going to be 120. I don't really like that number. That's going to make that too hard. Let's change this a little. Just because of the scale I drew, let's do it to, let's just say it's 2, okay? That'll be a little easier. You'll understand how to do the hard stuff after. Let's say it's 2. That changes it to 180. Well, that works out perfectly with my scale, okay? So what's happened now is my period is now 180 degrees, okay? So in other words, I'm going up here, down here, down here, and then at 180 I've completed a period. So this is what the function is going to start to look like. It's been compressed immensely, by a factor of 2 in fact. So I go up again, down again, down again.
How do you know it's like in between though?
Because I've done it in half. I've done 2. A way that we can prove all of this, if you ever get stuck and you really don't know what to do. Okay, well, let's prove it. You can always do this at any point with a calculator. Let's just say I wanted to find that. Oh, I don't have to do a calculator. No, technically we can do this. Say we're at 180, okay? If I'm to plug 180, actually I already know where that is. What's in between 180? We had 90. Let's do 45, because technically 45 is where I'm hitting the 1 here. So if I have 45 times 2, and then I sine it. So I go 45 times 2, because that's what I have, my 2x. Okay, 90. So I need to do sine of that. So I do sine of 90, 1. So there we go. There's my y point. Whenever I'm going across the x-axis, I can always plug numbers in for x and find out what their y is. I just have to do it properly. It'd be nicer if I had a calculator like yours where you could write all the way across. Those are a lot easier to do with. So for instance, in the same idea, let's say we had that same thing. Say I had 540 times 2. So I had 540 times 2, 1080. I got to find sine of that. Sine of 1080? Well, it's 0. So at 540, I'm at 0 again. So I can technically find every in-between if I want. Like I could find at 1. 1 times 2. So this is at 1 degrees. Sine of 2. 0.03. So I'd get really small down in there, okay?
I'm getting for 90. I'm getting 0.
Yeah.
But it says -1.
Because this is between. This is our 90 right here. This is halfway between 180.
But when I calculate it, I get 0.
Yeah. This is 90.
Isn't that 90?
0, 90, 180. This is 180, remember? In between 90 and 180 is 270. This is, or sorry, not 270. It's if it's a 90 degree 45, 135. This is at 135. Try plugging in 135. All right. -1.
But how do you know that it's 130? Like, how am I going to know 135 has a point?
You have to think of, because of the way I've scaled this, you have to think of what would be halfway between 180. Because here's 0, here's 180. What's halfway between? Well, it ends up being 90. And then if I want to go halfway between that, well, what's halfway between 90 and 180? I calculate it's 135. If I want to go halfway between that, I could find this point and this point. Like, you could technically find every single point by plugging in your calculator. We do it this way just because it's easier to graph. Okay?
Yeah.
You could do every single degree. It would take you forever.
Yeah.
Does that make sense?
Yeah.
Okay, so you realize that this is going to be squished, right? Let's do another period. Another period, let's do g at x equals opposite. A half. Oh, I wrote that wrong. Sine a half x, okay? Sine 1/2 of x, okay? Complete opposite. If I do 360 divided by a half, I'm going to just turn it into a decimal quickly. It's 0.5 as a decimal. That's going to give me 720. So my new period is 720. I wish I could have erased the green. I don't want to get you confused. I'm going to draw it in blue, okay? So I'm going to do the 720 period in blue. So what happens here is here's our 0, and I know my whole period occurs over 720. Okay, so I could find all my new spots by typing them in the calculator. Let's find out what 180 is. So you would have to do 1/2 of 180. 80 divided by 2, or times 0.5, same thing. And then sine of that. 1. So here we go, we're at 1. What about at 360? Half 360. Zero. Okay, so we're back at 0. Let's do 540.
-1.
-1. Okay, and then 720. 0. Okay, so if you notice now, compared to our black one, which was the original, the period has changed. It's much wider now. I know I drew that really straight looking, but the period has doubled in length. Yeah. Okay, that's the whole idea. The period compresses or it gets a lot wider.
Okay.
Okay, now you can technically put all 4 together. You can have a stretch with a compression that's been moved up and down and left and right. So it becomes complicated when you do all 4. Okay, but does those ideas make sense?
Yeah.
Okay. Let's stop this video here.